Welcome to the second presentation in the Introduction to GPS. We will begin by discussing how many satellites are required to determine our location on Earth. So let's work through that. If we have just one satellite, there is a circumference from the satellite to the Earth which would be the same distance all the way around. This means that rather than having one point on Earth, which is the exact distance to the satellite, there is actually a circle on Earth, which is the exact distance to the satellite. So we need more than one satellite. If we have two satellites connecting to the GPS receiver, then we have two circles around the Earth, each of the same distance from each satellite. Where they intersect is the possible location of where the GPS receiver could be. This is shown in the yellow shaded area. This is quite a large area, not precise at all. So we do need more than two satellites. If we have three satellites that intersects the previously yellow shaded area, we find that there are 2 points of equal distance to the third satellite. So our GPS receiver could now be on either one of the yellow points highlighted in the diagram. A fourth satellite allows us to connect with one of those 2 points identified by the third satellite. This will give us our exact location. Hence, to determine our GPS location, we need at least 4 satellites to determine. More than 4 is better. The more satellites we have, the more precise our location will be. Now that we know we need 4 satellites to determine our location, does it matter where those satellites are positioned in the sky? What you can see here is called a sky plot, and each dot is a satellite with its number, and each line is the orbit of that satellite. There are various ways we can get inaccuracies due to where the satellites are placed in the sky. The first one is called the H-DOP, or the horizontal dilution of precision. There is also a V-DOP, which is the vertical dilution of precision. We also have a G-DOP, called the geometric dilution of precision, and the P-DOP, called the positional dilution of precision, which is a combination of them all. Our GPS receivers can also show us sky plots of which satellites they are connecting with and where they are positioned in the sky. There are 4 quadrants that we see in the sky plot, and there might be any combination from sky plot 1, 2, 3 or 4 that our GPS receiver will show us. We will now discuss how these geometries affect the dilution of precision for our locational information. Our horizontal dilution of precision is affected mostly when satellites appear in only 1 or 2 of the quadrants. A poor horizontal solution will result in a high H-DOP number. Ideally, the satellites should be spaced over the 4 quadrants. A good horizontal solution will give us a low H-DOP value. Our vertical dilution of precision is affected mostly by the angle of the satellites in the sky. So where it is close to the circumference of our sky plot, our satellites are very low on the horizon. We usually insist on our receiver having a curtain of 15 degrees above the horizon. This means that it will not detect satellites 15 degrees or less below the horizon. Satellites low in the sky give a poor vertical solution or a high VDOP value. Again, we can see that satellites well spread over the 4 quadrants and not too close to the edge of the horizon will give us a good vertical solution, a low VDOP value. The geometry of the satellites refers to how close they are as well, not just if they are evenly spaced over the quadrants or if they are sitting low on the horizon. We don't want them too close together, high above us either. That will give us a high GDOP value and a high geometrical dilution of precision. Ideally, satellites that are well spread out, not too close to the horizon, with one overhead will give us a great geometrical solution or a low GDOP value. PDOP values range from 1 to more than 20. 1 is ideal for applications requiring the highest precision, such as precision agriculture. 1 to 2 is accurate enough. 2 to 5, anywhere from 1 to 5 we can use for handheld GPS units. Anything above 5 is not giving us a really good location. Anything above 10 probably shouldn't be used. This chart shows us how the PDOP values vary with the time of day. On the y-axis we have PDOP values from 0.6 to 3. Going back to our previous slide, all of these values shown are good enough for a handheld GPS unit, as they are all under 5 or 6. We can see though that there are some times of the day shown on the x-axis that are better than others, say about 5 o'clock in the evening or 11 o'clock. There's other times that are not so great. All the lines that we're seeing, just to summarise, the PDOP is a combination of the vertical and horizontal dilution of precisions. To summarise for now, to accurately determine our location, we need at least 4 satellites. They must be 15 degrees above the horizon. There will be poor horizontal dilution of precision if the satellites appear in only 1 or 2 quadrants of the sky plot. There will be poor vertical dilution of precision and geometrical dilution of precision if the satellites are either too low in the sky or clustered together. With respect to PDOP values, smaller is always better, and 5 or less for handheld GPS.